Yes.
And the talks about increasing engagement with interactive visualization, formal methods as serious games.
Yeah,
please go ahead.
Thank you. So, I'm going to talk about an interactive visualization tool for one of the lectures that I have been DA for, and this is joint work with Lukas Grätz from Darmstadt, where the course was held. So the course that I'm talking about is the automated theory improving course, which is held by Professor Haenle, where I was responsible for the exercises. And this course is a master level course, which is teaching several automated theory improving techniques to the students so they can understand how the theory improvers work and possibly implement their own. But this is all automated, not interactive theory improving. So for example, we teach them Tableau, resolution calculi, DPLL, and so on. And the problem when we had the exercises was that there was a very big gap between how we present the algorithms and the representation and how we implement them and use them in the exercises. So we use all these nice drawings of Tableau trees, for example, in the lectures, and then we give them an automated theory improver, where there is no tree at all, or maybe it's a textual tree, which you have to somehow find in the implementation. So we had the problem that we want to teach them and to use them, these algorithms, but at the same time, they had to make two conceptual steps. They not only have to transfer it to a different setting, they also have to change the visualization. So we often ran into the problem that they complained about not having enough examples which show a certain kind of Tableau proof, because there's not that much material on it. And you can't just generate new examples and look at how the tree looks like if you use an automated theory improver, because it does not output you the tree. And if you output it, it will output its internal representation. So what we wanted to do is to increase the tool so we can engage the student more, that the lectures become more interactive, and especially that the exercises are tighter bound to the lectures. And then we found that we wanted to do it properly. So how do you design this tool? How do you integrate it in this lecture? And following Martin's talk, which I fully agree with, there was very little theory on why a tool in a formal methods course or in a logic course was working. There are a lot of experience reports that describe how a tool is working, that describes how it is applied, but there is very rarely some kind of discussion of what parts were successful and which were not. And very often this is highly specific to the course. It is very different if you teach this kind of course where the students have seen 4 or 5 formal methods lectures already, or whether we teach it to beginners. So what we did is that we looked at different fields and disciplines and how they do this kind of thing. And then we tried to develop the tool coming from their perspective. And indeed, in this talk, I will not so much talk about the tool that we developed. I will also do that in the end, but I also want to talk about how other fields are doing this and how we can apply their taxonomies to our systems. So the tool that I present will be about logic, but I think it can be applied in a more general formal method setting, where under formal method, I quite broadly understand something that has syntax, some kind of semantics, and some kind of rules which operate on the syntax and not on the semantics. For example, for logics, we have our sentences defined by grammars, we have the models and some satisfiability relation, and we have proof systems which operate on our formulas or some other representation of it. The first thing that we looked at were serious games, because there's a lot of educational theory behind serious games, and like proper trial studies, how it helps. And one possible definition of serious games is that it's an interactive system based on a set of rules which are directed towards a goal and provide feedback to the player to monitor progress. So this is not that far away from formal methods. So obviously we have some kind of state, we have some kind of rule, and we want to do something with the rules. So we want to close a proof, we want to show that we cannot reach a certain state, we want to reach a certain state. But this provide feedback thing was maybe a bit lacking in most of the formal methods tools as you look at, and the one that we develop ourselves. And here we came back to this problem that we want that they have the same representation that we use in the lectures as when they do their exercises. And we do very visual representation of proof trees. Indeed, we use them as trees. And if you have auxiliary structures, we also visualize them. So what we need is to turn a formal method into a proper serious game is to have an interactive visualization, where we can interact with the system by choosing rules, for example, or choosing subformulas where to apply a certain. So thankfully, people have also done a lot of work on program visualization. So program visualization, and they also have a theory of why it works, which they call the epistemic fidelity theory. And they say that visualizations provide a faithful account of an algorithm's executions in terms of an algorithm's expert's mental model. So note that here, what they talk about when they talk about teaching is that we are talking about the mental model. We are not talking about the implementation at all. It is only about the concepts. So we're teaching about how it works and not how to apply it. And what do I mean by algorithm visualization? So I have a very short example of what people did research on in that time. So I hope you can all see my YouTube video. So this is a visualization from the beginning of the 80s, one of the first ones that we found, where they have several sorting algorithms, which they execute in parallel. And you can see the one on the right is quicksort. You see how the algorithm splits it into halves and where it's split or not. And then the other ones are faster. And if you look in more detail, and the video is quite long, you will find out that one of them is insertion sort, I think, and the other one is bubble sort, I think. So great. So this is the kind of things that people looked in. It's not that different from our formal methods, except that most of the things they looked at are deterministic. And then they have done some studies whether it's useful or not. And then they found out it's not useful. They'll have like 20 studies, I think, and the meta study also by Hundhausen in the end concluded that they found that studies in which students merely viewed visualizations did not demonstrate significant learning advantages. They have also a proper definition of learning advantages, but the important point here is that just that we think that something is good for the students does not mean that we can measure the positive outcome of it. So what they did afterwards is that they looked into this in more detail and they said, okay, visualization technology, no matter how well it is designed, has little educational value until it engages learners in an active learning activity. And they defined what they mean by active learning activity. Right? So how do I engage the student if I have an interactive visualization tool? And they have this taxonomy of 6 steps, which are not building on each other, by the way. The last 4 are orthogonal. So you can not view it at all. You can view it, and then you can do these 3 things. And that we have seen there's no big advantage in going from not viewing to viewing. And then later, this is from the work of Miller, they have given examples how to engage student in one of the categories that is defined in this taxonomy. For example, for responding, they give examples. Okay, what's responding? A learner is presented with questions related to the visualization. And then they show how you can do this in different parts of course. For example, you can in the lecture ask, what's the next step? And then the student tells you the next step. And if you're interactive and you have backtracking, you can indeed just go down a wrong path to show why it's wrong. While this is often very hard to do if you do it on the table or very time consuming. You can ask them what's the relation to the code? What's the relation to the textual representation of the algorithm that you're giving? Or you can do the last step and ask them, was the step correct? If it was not correct, why not? Which rule selection strategy did I use? And so on. The next category is changing, where you modify the data which is visualized. For the deterministic algorithms, this is mostly changing the input. In our case, it's mostly which rule to execute next, because we are in very non-deterministic settings. This is, of course, also done in either lecture or the exercises, where it's probably more interesting for the exercises where they have to actually show you how to interact with the proof. The next part is constructing, where the learners are expected to create an own visualization. For example, if we go from standard resolution to set of support sets, how do you visualize the set of supports, right? And this engages the student in a completely different way than just implementing it, because they have to show it and have to think about how do I represent my mental model as well, not only how do I program it down. And the last stage is presenting, where they use existing visualization to discussions among others, among students, for example. Right. So if you present a lab, they have a big visualization, they have a big model, and you do something with it, and you use the visualization to explain it, which of course forces you to engage with the material in again a different way, because you are stuck with the visualization that you're given, and you must still navigate your own mental model of how you solve the problem. And this can be done, for example, to present labs, but also in exams. Sorry. So what we did is to develop this tool, which we call Calculera, which I will show you in a moment. And there are two core concepts in it. The first one is what we call an epistemic thread, which means that this tool is used throughout all the course elements. It's used in the lectures, in the labs, in the exercises, and if you want, you can use it in the exam on the same abstraction level that is given in the lectures. So that the student does not have to make this context changes, let's call it, when going from one part to another. So if you want to implement something, you want to visualize it, you don't want to use some completely unrelated program with a different internal representation. So we use it in lectures, or you can use it in lectures. I think last year it was used to present some examples and questions in the lecture. So it's the same visualization that can be used in exercises. We use it to give them exercises, which they can upload the solution as input to the tool. We found it very useful, I think, to give it to the students for self-study, because they can execute their own example and get feedback why it's wrong, instead of doing the proof by pen and paper and not realizing that they're doing wrong steps. And you can also use it in labs, for example, to implement strategies. Sorry, so this is calculierbar. This is a live instance. You can go on it under kbar.app. Please don't do so now, so you don't break the server where I'm presenting. And it's an open source implementation. So you can go here, download it, and running it is as simple as typing run, which starts a web server with the interface that I have shown you. Sorry. So we have implemented several kinds of calculus. So we have Tableau for propositional logic, for FO, non-clausal Tableau, and for model logic, DPLL, 2 ways of propositional resolution and 2 ways of the sequence calculus. So let's look at the propositional Tableau just to give you a feeling on how the tool works. And does this work? Yep. So what you can see here is an explanation of the syntax. Then you can enter a formula, and then you can choose what kind of Tableau you want to have. For example, you want it strongly connected and regular. And it's not that important for the talk what regular means or not. Then you can start the proof. You get a nice tutorial. So this is something which we got from the serious game sites, right? That we get this small videos playing here. And you can also reactivate it here, which also explains you the rules. And I think that this is a way towards gamification, because in the end, these systems, they are more simple than, let's say, Candy Crush. They're just less colorful and less fancy to do it. So let's make a Tableau proof. You click on the node, you click on one of the clauses, and then you get the tree underneath. And now you can, of course, ask the students, oh, what will happen if I click on this node and try to add this clause here again? And now the system will tell you, oh, you can't do this. Why can't you do this? Because you would introduce a duplicate node. The node will be umbrella, and then the tree would be irregular, right? So this would like say, okay, you're trying to do a regular Tableau, but you're breaking it now. So if the student would have not understood what regular means, the system would tell him very clearly what it does and why it is not regular afterwards. So if you click further, you can then close the proof and so on. So I will not finish the proof. I don't think that it's that interesting to prove this formula. You can also download the solution or the tree that you have, so you can communicate it to the TA, send him, oh, I have a problem with something. Can you help me? This is my proof status and I cannot solve it for some reason. So this is used in the exercises. You can see it's very easy to go through examples if you are in a lecture here as well. So you can undo something and say, look at some other rule selection strategy. Tableau is quite easy to visualize in the sense of that's how most people visualize Tableau. I later found out that if you do resolution, there are a lot of ways to represent it. And so, for example, you can show it in a cycle, or you can just have it as a set where you have the set of clauses here, and then you click between them and get another representation. I later found out that people also represent resolution as a tree, but we have not implemented it. This would indeed be a nice lab in the category of extending the visualization to show how this is in the tree-like structure and where the proof follows there. So the tool has no strategies implemented, it's purely interactive, so you cannot just say auto, but one possible lab would also be that the students implement different strategies and then also implement the visualization of the strategies. The tool is implemented in Kotlin and TypeScript, where all the technical part, let's say, is in Kotlin, and TypeScript is only used for the visualization. And maybe a last part, this is responsive design, meaning you can run it on your smartphone and click it with your fingers. Also during the lectures, because some students, before they answer, they want to like play it around and see, oh, I have tried this. Can you explain why this rule doesn't work or something like this, which you can do live on the lecture. And you don't have to have your laptop open. So if I would have been in Beijing, I would have given this talk completely on my smartphone. It's sadly not possible here. So what have I talked about? I have now shown you Calculierer, but this is an implementation of multiple PL and FO-proof Calculi, and I hope that it's easier to use in your lectures than it is with some other tools, in the sense of that it's very easy to run. And then the paper describes quite a few ideas on how you can implement it in different stages of your course and why we think it works. And this why we think it works is now rooted in educational theories from interactive program visualization. It is, of course, the question whether you can just apply theories from them in our field or not. And we hope to see some more didactic-oriented, structured exposés on formal methods teachers in the future. And we also hope that we will see some more proper trials on the tools and lectures that we have, because as we have seen with the visualization, just that we think it works does not mean that it indeed increases some kind of learning outcome. So the main conclusion here is use our tool if you want, and you can already have some didactic structure for formal methods teaching. It's just that you have to look a little bit outside and see formal methods from a different perspective. Thank you.
Thank you very much, Eduard. That was a great demo and a great presentation. Were there any questions from the audience? If so, please feel free to raise your hand or type it in the chat. If not, maybe I could ask one. I was wondering if you'd sort of tried other things like, verification, or like program verifications, for instance, Hoare logic or something like that, using the tool?
No, because the course is only about automated serial improving for first order logic. So in the program verification course that is also taught at Darmstadt, the key system is used, which you can probably analyze from the same point of view and see which categories are used and where is the visualization good. Can you see it as a serious game or not? And how do you integrate it if it is a serious game? But we haven't done this. We have only looked at Calculierer from this perspective. Yeah.
Okay. So we've got a couple of questions. We've got a comment from Cliff, first of all. Cliff, would you like to expand on that?
No, it was just a comment relating to the impact of visualization, and it helps some students and not others.
Okay. Would you like to expand on that a bit more, or was just were you just pointing out that book?
I was really just pointing out the book. What Keith did was a careful study of a tool from Stanford, I think, and they used it with all of the students. Because it was from the professor, every student said they found the tool useful. They actually measured the outcomes, and it helped half the students and didn't help the other half. It relates to Eduard's point about you have to be careful about the impact of visualization tools.
Okay, I'm not aware of the book, but I will have a look. Thank you.
Okay, we've got a hand up from Zhao.
Okay, thank you. And thanks for the talk. The system seems really, really nice. So my question has to do with this notion of serious game. So from my understanding, there's a lot of work on serious games and gamification applied to learning and teaching. And there are many aspects that are not yet considered by your system. So for example, typical things that we use in games, like encouraging competition, in this case, among students, and giving badges, different types of badges. So there are many things I believe that could be used to extend your system. And my question is if you have considered any of these as future work, and is it worth it in this context? Do you have any ideas on that?
Yes, yeah, thanks. So we have looked into gamification. We have implemented almost nothing, but only because we didn't have the time. We did have ideas about giving some optional exercises and then having a high score where the student with, like uses the subset of Tableau and still has the shortest proof, get some additional points or something like this. I think it's a good instrument also to let the students try out different proofs for the same formula. So to guide him to like getting more points, to motivate him to look at the same system again. In general, I think it's a good idea also to integrate it with tools like Moodle or Canvas, where you can then just export it and see how's the progress in point-wise in for your exercises. So gamification is a thing that's looking into, yeah.
Okay, thank you. Just as a brief comment, so we have a system here in my university that was created by our team. And one of the things that I mean, it's not about formal methods, it's a general system, but something that it allows students to do is to create their own tournaments. And we noticed that some students really like that because they can compete amongst themselves. And the nice thing about it is that they have to create the questions and they have to create the problems. And that entails a lot of understanding. So maybe a suggestion for your system.
That sounds interesting, thank you.